Imagine for a moment standing at the edge of a cosmic precipice, peering deep into the very heart of our Milky Way galaxy. A region so remote, so veiled in mystery, that for centuries it was the stuff of both ancient lore and the wildest scientific dreams. For generations, humans gazed up at the hazy ribbon of our galaxy, seeking answers about the power hidden at its core. Today, thanks to an extraordinary blend of human curiosity, determination, and cutting-edge technology, we are finally lifting the veil on this cosmic engine, and what we are discovering is nothing short of mind-bending. What if I told you that, in the not-so-distant past, the galactic center unleashed an eruption so astonishingly powerful that its aftershocks still ripple across tens of thousands of light-years? This outburst left behind gigantic scars, colossal, glowing structures unlike anything else in our galaxy. They are called the Fermi bubbles. These aren't just silent relics of ancient chaos. They are active, dynamic clues, continually challenging everything we thought we knew about galaxy life cycles, star birth, and even the delicate balance between order and chaos in our universe. What really happened in the Milky Way's concealed core? Could another eruption still be in our future? And what does this cosmic drama mean for us, orbiting a modest star on the galaxy's calm outskirts? To answer these questions, let us journey to the very center of the Milky Way. Here lies Sagittarius, a star, a supermassive black hole, its mass exceeding 4 million times that of our Sun. For billions upon billions of years, this gravitational titan has shaped the fate of our galaxy. The galactic core is a cauldron of unimaginable energy, swirling matter, fierce radiation, and crushing gravity locked in an endless dance of creation and destruction. Stars are born in dense molecular clouds, only to be destroyed by supernovae or torn apart by the black hole's relentless pull. The history of this region is a saga, written in cycles of violence, renewal, and transformation. The dawn of the 21st century brought a revolution in our understanding of these cosmic forces. In the year 2010, using data from the Fermi Gamma-ray Space Telescope, astronomers made a discovery that sent shockwaves through the scientific community. They unveiled two gargantuan balloon-like structures, enormous lobes of high-energy plasma, each stretching 25,000 light-years above and below the galactic plane. Together, these Fermi bubbles span an astonishing 50,000 light-years. To put that in perspective, if one bubble were placed end-to-end with another, they could nearly stretch from our galaxy's core to its farthest reaches. Imagine a pair of cosmic lanterns, so enormous and radiant that they would dwarf every known structure within the Milky Way, glowing fiercely in high-energy gamma rays. A wavelength invisible to human eyes, but blazing in the view of our most advanced instruments. Yet the story does not pause there. Further probing with X-ray telescopes, such as the revolutionary eROSITA observatory, revealed even larger formations, the eROSITA bubbles. These extend far beyond the original Fermi bubbles, painting a picture of an even more dramatic and violent past for our galaxy. The eROSITA bubbles are like vast, shimmering curtains of X-ray light, enveloping the galaxy and hinting at explosive events that shaped not only our home, but the very structure and composition of the Milky Way itself. These discoveries forced scientists to rewrite the narrative of galactic evolution. It became clear that these outflows of energy and matter phenomena, known as galactic feedback, are not rare, isolated occurrences. Instead, they play a crucial, ongoing role in regulating star formation, redistributing gas, and sculpting the grand architecture of the galaxy. So, what could possibly create such cosmic spectacles? The leading theories point to two dramatic possibilities. The first involves Sagittarius A star itself. Imagine the supermassive black hole experiencing a feeding frenzy, devouring vast clouds of interstellar matter. In a process called accretion, this infall of matter releases jets and winds of energy, powerful enough to sculpt these gigantic bubbles. Alternatively, a period of furious star formation, a galactic starburst, might have ignited waves of massive stellar winds and supernova explosions, collectively blasting hot gas and cosmic rays into the galactic halo. In either scenario, the energy released is almost beyond comprehension, rivaling the combined output of millions of exploding stars, each one itself a cataclysmic event. But as so often happens in science, a new discovery upended expectations and deepened the mystery. With the help of the Green Bank telescope, one of Earth's most sensitive radio observatories, researchers zoomed in on the Fermi bubbles and found something that defied logic. Embedded within these superheated million-degree Kelvin structures were pockets of cold, dense gas. These clouds, composed of neutral hydrogen and weighing thousands of times more than our Sun, were suspended a staggering 12,000 light-years above the galactic core. The analogy is irresistible. Finding these cold clouds inside the Fermi bubbles is like discovering ice cubes floating in a volcano's molten heart, as Andrew Fox, an astronomer at the Space Telescope Science Institute, so eloquently put it. Finding those clouds within the Fermi bubble is like finding ice cubes in a volcano. Why is this so astonishing? According to our most advanced computer simulations, cold clouds like these should not survive for long inside the blistering heat of the Fermi bubbles. The searing temperatures and violent winds would be expected to evaporate any cold gas in just a few million years, a mere blink on the cosmic timescale. Yet here they are, stubbornly persisting. How can this be? The answer, it turns out, lies in the surprising speed of these cold gas clouds. Astronomer Rongmon Bordeloi and his team measured the velocities of these clouds and found them hurtling through space at up to 2 million miles per hour. This immense speed, coupled with the cloud survival, suggests that the Fermi bubbles and the eruption that created them are far younger than once thought, possibly less than 10 million years old. In the life of the universe, that is practically yesterday. To truly grasp this, consider where Earth was when the Milky Way's core last erupted. The dinosaurs had already disappeared. Mammals were flourishing and diversifying, but the earliest human ancestors were not even a glimmer on the evolutionary horizon. In cosmic terms, the birth of the Fermi bubbles is a recent event, nearly contemporary with the world we know. As Bordeloi remarked, these clouds weren't here when dinosaurs roamed Earth. In cosmic timescales, a million years is the blink of an eye. This realization raises profound questions. What kind of event could unleash such incredible energy? Enough to sculpt the structure of the galaxy, yet leave behind delicate remnants of cooler, quieter epochs. If the Fermi bubbles are indeed the aftermath of a recent outburst, what does that mean for the Milky Way's future? Are we living in a time of rare, tranquil calm between cosmic storms? Or could another eruption already be brewing, hidden by the swirling dust and magnetic fields at the galaxy's heart? The debate among scientists is lively and far from settled. On one side, compelling evidence points to Sagittarius A star as the primary culprit. Researcher E. Coretti has highlighted the surprisingly organized magnetic fields within the Fermi bubbles, suggesting a single, coherent explosion rather than a string of random outbursts. This supports the notion that the supermassive black hole periodically awakens, devouring matter and releasing jets of energy that ripple across the galaxy. Imagine a flash of unimaginable brilliance at the galactic center, a cosmic beacon so powerful it could be seen across intergalactic space, sending shockwaves that shape the birth of stars, the formation of planets, and perhaps even the emergence of life itself. Yet, other experts propose that an epic starburst event, an era when countless massive stars were born in rapid succession, only to die in spectacular supernova explosions, could have powered these bubbles. Starburst galaxies elsewhere in the universe show similar vast outflows, driven by the combined force of stellar winds and supernovae. In both scenarios, the energy required is truly staggering, enough to heat gas to millions of degrees and accelerate it to velocities that test the limits of our understanding of galactic dynamics. The discovery of cold clouds within the Fermi bubbles adds a fascinating new layer of complexity. These cold clouds may be relics, swept up from the galactic center and carried aloft by the hot wind that formed the bubbles. Jay Lockman, an astronomer at the Green Bank Observatory, explains, "Just as you can't see the motion of the wind on Earth unless there are clouds to track it, we can't see the hot wind from the Milky Way, but can detect radio emission from the cold clouds it carries along." This realization has opened a new frontier in galactic research. By using these cold clouds as tracers, scientists are beginning to map the invisible flows of energy and matter throughout the galaxy, uncovering the hidden dynamics of cosmic feedback. These discoveries are not just academic curiosities, they have far-reaching implications. They challenge our foundational models of how galaxies evolve. Feedback from black holes and starbursts is now seen as central to shaping the structure and destiny of entire star systems. Computer simulations, which once assumed uniform outflows and simple dynamics, must now grapple with the complex interplay of hot and cold gases, tangled magnetic fields, and high-energy cosmic rays. The persistence of cold clouds in such a hostile environment places strong empirical constraints on these models, forcing scientists to rethink how energy and matter cycle through galaxies. But what does all this mean for us, living on a planet some 25,000 light-years from the galactic center? Should we be concerned about future eruptions? The reassuring news is that the energetic outflows associated with the Fermi bubbles pose no direct threat to our solar system. We reside safely in one of the galaxy's spiral arms, well beyond the reach of these cosmic winds. Nevertheless, the broader consequences are profound. Understanding the history and mechanics of the Fermi bubbles offers vital insights into the processes that govern star formation, the distribution of elements, and the emergence of habitable worlds, not just in our own neighborhood, but throughout the universe. For those fascinated by the intersection of technology, economics, and cosmic phenomena, the Fermi bubbles offer a powerful analogy. They are natural examples of feedback loops, self-regulating systems where energy and matter are cycled through bursts of intense activity and long periods of calm. Just as economies experience booms and busts, with shocks and recoveries shaping the trajectory of nations, galaxies undergo cycles of explosive change that reset the conditions for future growth and evolution. By studying these cosmic feedback mechanisms, scientists are developing new models and simulations that have applications far beyond astronomy, informing everything from climate prediction to artificial intelligence and the design of resilient technological systems. The lessons learned from the Milky Way's tumultuous past echo in the innovations that drive progress here on Earth. Let us take a closer look at how these discoveries have revolutionized astronomical research and inspired entirely new generations of scientists. The detection of the Fermi bubbles was only possible because of the remarkable synergy between different observatories and advanced technologies. The Fermi Gamma Ray Space Telescope, launched in the year 2008, provided the first glimpse of the bubbles through its sensitive gamma-ray vision. Later, the eROSITA mission, with its advanced X-ray detectors, revealed even larger structures, offering a multi-wavelength view of the phenomenon. Ground-based observatories like Green Bank brought unprecedented sensitivity to the study of radio emissions, enabling astronomers to trace the cold hydrogen clouds within the bubbles. The Hubble Space Telescope added its own ultraviolet observations, detecting highly ionized, multi-phase gas, and confirming that cold clouds are being evaporated by their hot surroundings, evidence of a dynamic, multi-phase environment. Each new observation has forced scientists to refine their theories, adapt their models, and pose fresh questions. How do magnetic fields organize themselves within these gigantic structures? What is the role of cosmic rays in shaping the bubble's evolution? How does the interplay between hot and cold gas influence star formation in the galactic disk? These questions have spawned a wave of computational simulations, harnessing the power of supercomputers to model the complex physics at work in the heart of the Milky Way. Recent simulations have even begun to account for the effects of turbulence, magnetic reconnection, and the intricate dance of cosmic rays, a level of detail that would have been unthinkable just a decade ago. Looking ahead, the future of galactic research is brighter than ever before. The James Webb Space Telescope, with its unparalleled infrared capabilities, is poised to peer deep into the cold hydrogen clouds, tracing their structure and evolution with unprecedented precision. The Event Horizon Telescope, which has already captured the first-ever image of a black hole shadow, may soon provide new insights into the current activity of Sagittarius A star. Next-generation gamma-ray observatories will map the high-energy emissions of the Fermi and eROSITA bubbles with greater clarity, while advanced simulations will model the complex interactions between the galactic core, the bubbles, and the vast surrounding halo. These collaborative efforts promise to unlock new secrets about the origins, evolution, and ultimate fate of our galaxy. Historical parallels abound. Time and again, unexpected discoveries have forced astronomers to rethink their most cherished assumptions. When Edwin Hubble revealed that the universe was expanding, it overturned centuries of belief in a static cosmos. The discovery of the cosmic microwave background radiation in the 1960s offered the first direct evidence for the Big Bang. The revelation of the Fermi and eROSITA bubbles, with their enigmatic combination of hot and cold gases, may herald the next great leap in our understanding of how galaxies live, evolve, and ultimately die. Just as previous scientific revolutions reshaped our worldview, the true significance of these discoveries may only become clear with time, continued observation, and the relentless pursuit of knowledge. We must also remember the human dimension of this cosmic tale. The story of the Fermi and eROSITA bubbles is a testament to the power of curiosity, teamwork, and perseverance. Teams of scientists from every corner of the globe, engineers, physicists, astronomers, computer scientists, have come together to solve one of the universe's grandest mysteries. Their work is a vivid reminder that, even in an age of rapid technological change and economic uncertainty, the quest to understand our place in the cosmos persists. Every new discovery, every fresh insight, enriches our sense of wonder and possibility. But what is the ultimate takeaway from this extraordinary cosmic saga? The revelation that cold clouds can survive within the fiery embrace of the Fermi bubbles turns our understanding of the Milky Way upside down. It tells us that our galaxy is not a static, unchanging backdrop, but a living, evolving ecosystem, one that is prone to sudden, extraordinary events. These outbursts are not just echoes of a distant past. They remind us that the forces shaping the cosmos are still at work, and may yet surprise us in ways we can scarcely imagine. If you have ever wondered what truly determines the fate of galaxies, or whether our own Milky Way could still amaze and astonish us, the answer is a resounding yes. The next great eruption from the galactic center might be millions of years away, or it could already be brewing, hidden within the swirling clouds and magnetic fields at the heart of the galaxy. As we continue to explore, to observe, and to dream, we become participants in an ongoing cosmic story, one that connects the birth of stars, the power of black holes, and the fragile emergence of life itself. Before we close, let us return to the practical implications, the ripple effects of this research in our own world. By studying the complex feedback loops in our galaxy, scientists are developing new ways to model turbulent systems here on Earth, from weather and climate to financial markets and artificial intelligence. The lessons of cosmic feedback, the interplay of order and chaos, stability and disruption, are shaping how we approach resilience and adaptability in our own global systems. The universe is not just a laboratory for understanding the stars, it is a mirror reflecting the challenges and possibilities we face as a species. If you found this journey into one of the universe's wildest mysteries as enthralling as I did, be sure to subscribe and ring the notification bell for more stories about the forces shaping our universe and our future. And here's one final thought. By unraveling the story of the Fermi and eROSITA bubbles, astronomers are inching closer to answering some of the deepest questions in modern science. How do supermassive black holes grow and influence their host galaxies? Why does every galaxy, including our own, harbor one of these cosmic titans at its center? What role do these giants play in the grand tapestry of creation, evolution, and destruction? Stay curious, keep exploring, and remember, the universe is always ready to surprise us.